All right, so we're going to find the derivative of this expression implicitly. We're going to find dy dx, or the derivative of y with respect to x. When we're doing this, we're imagining that y is a function of x. So when I differentiate x cubed, x is just my nice variable. The derivative of x cubed is going to be 3x squared. But then the derivative of y squared, that's like differentiating some stuff squared. So we're going to get 2 times our stuff to the first power. Normally I wouldn't write that, but it's good to write it. Then we have to multiply by the derivative of the stuff, which is dy dx. Over here, we have x times e to the y. That's a function times a function. X is a function of x. E to the y is a function of x. So we have to use the product rule here. So the derivative of x is 1 times e to the y. Plus, now we switch it up. We leave the x alone. We multiply by the derivative of e to the y. The derivative of e to the x is e to the x. The derivative of e to the stuff is e to the stuff times the... Thank you, the derivative of stuff. So the derivative of e to the y is going to be e to the y times the derivative of y. Equal to the derivative of 7. Yes. Now we do the algebra. We solve for dy dx. I'm going to leave these terms with dy dx on one side and bring the other terms that don't have it to the other side. So I'm going to write this as 2y times dy dx plus x times e to the y times dy dx equal to negative 3x squared minus e to the y. I'm going to factor out the dy dx. I have dy dx times 2y plus x e to the y equal to negative 3x squared minus e to the y. And finally, I divide both sides by whatever's multiplying dy dx to get dy dx all by itself. So dy dx is going to be negative 3x squared minus e to the y all over 2y plus x e to the y. And normally I would leave it like this, but I'm going to factor out a minus sign from the top just to see the formula that we actually want to see here. So I'm going to rewrite this as negative 3x squared plus e to the y over 2y plus x e to the y. And that certainly works. It's a perfectly fine way of taking an implicit derivative whenever you're doing this kind of process. However, the chain rule does give us an alternate formula. Let me show you what I mean. So to do this, we're going to make one small change. So we're going to take our equation, x cubed plus y squared plus x times e to the y equal to 7. And we're going to bring everything to one side. So I'm going to bring typically to the left, although it doesn't really matter. So that you have something equal to 0. And we're going to call this something on the left-hand side. We're going to say that's a function of our variables, x and y. So I'm going to say this is capital F of x comma y. So I want to point out that F, capital F, depends on both x and y. And x and y both depend on x. Or at least we're pretending that they are. Right? We are operating under the assumption that x is our independent variable, and we're going to differentiate with respect to x. Well, great. We can use the chain rule. If I have that capital F of xy is equal to 0, then I can differentiate both sides with respect to x. Notably, the derivative of the right-hand side is going to be 0 still. On the left-hand side, well, chain rule. So I'm going to do del f del x times dx dx plus del f del y times dy dx equal to the derivative of 0, still 0. Questions about this so far? Just using the chain rule. Okay, now I'm going to do a little bit of rewriting. I'm going to rewrite dx dx as 1 because the derivative of x with respect to x is 1. And I'm going to rewrite del f del x and del f del y as capital Fx and capital Fy, just because that's pretty standard notation. So I'm going to rewrite this as capital Fx times 1 plus capital Fy times dy dx. That is a dy dx equal to 0. And now I'm going to solve for dy dx. So capital Fy times dy dx is equal to negative capital Fx. If I divide both sides by capital Fy, I get the dy dx is equal to negative Fx divided by Fy. That's the formula. That's I mean, I think that's actually formula equation 3 or 5 or something. The more general one we'll talk about in a second here. But this is the idea. So let's actually look at the thing we're looking at, our f here, and see if it gives us the same answer as before. So if I look at this, dy dx should equal negative, let's see. So looking at this here, the partial derivative of my capital F with respect to x is going to be the derivative of x cubed is 3x squared. The derivative of y squared is 0. The derivative of x times e to the y is 1 times e to the y. The derivative of 7 is 0. And the denominator, I'm going to have capital Fy. Capital Fy, the partial of f with respect to y is going to be 0 plus 2y plus the derivative of x times e to the y is x times the derivative of e to the y, which is still e to the y. Notably here, we're not pretending that y is a function of x. We're just saying that y is its own variable. So taking the derivative of f with respect to y. Is that the same as what I had before? Looks like it. That and that, same thing. This is the shortcut version of the chain rule formula when you know how to do this multivariable differentiation. So more generally, if you have like a function of 3 variables, for example, if we have capital F of x comma y comma z equal to 0, then you can find any partial derivative you want implicitly by using this formula. So for example, del z del x is going to equal negative fx over fc. You always flip where the letters are. So if you have z on top and x on the bottom, over here you have x on top and z on the bottom. It's a negative up front. And every other formula works exactly the same way. Del z del y would be negative fy over fz. Del y del x would be negative fx over fy. We could go on. I guess we could write them all. Del y del z would be negative fz over fy. Del, I don't know, x del y would be negative fy over. I don't think you need to actually write all these. And then finally, the last one would be, I don't know what, del x del z, sure. It's always just negative. That variable goes on top. That variable goes on the bottom. So whenever you're asked to find any of these derivatives implicitly, you can instead use equation 4 or 5 or whatever is in the textbook. So for another example, sure. Let's say we have given that, I'll change this one up, yeah. Let's say we're given x cubed y to the 4th times z squared equal to 8 minus x times cosine of y plus z cubed. And I'm asked to find 2 things. I want to find del y del x. And yeah, it is appropriate to say y del here, because since there's a 3rd variable here, it's going to always be a partial derivative. And let's also find del x del z. The first thing you have to do whenever you do this, you have to bring everything to one side. It's not an option. So I'm going to rewrite this as x cubed. I guess I should bring everything to the right, but I already started writing it this way, so well. x cubed times y to the fourth times z squared minus 8 plus x times cosine of y minus z cubed equal to 0. I will say, although it's not really important, and you should probably set equal to 0 every time, you could technically get away with leaving a constant on the other side, because the derivative of a constant is also there. So if you really, really wanted to for some reason, you could leave the 8 over there, although I wouldn't. You could. All right, so to find del y del x, it's going to be the negative of the partial of this. I should label this, right? This is my capital F here. Capital F of x, y, z. My del y del x is going to be the negative of the partial of f with respect to x over the partial of f with respect to y. So let's find that. So I'm going to put a negative out front. Looking at this whole thing, the partial of f with respect to x, I'm going to get 3x squared times y to the fourth times z squared. The derivative of 8 with respect to x is 0. The derivative of x times cosine of y is going to be 1 times cosine of y. And the derivative of z cubed is going to be 0. Again, I'm saying derivative, but I should really be saying derivative with respect to x. All right, let's fill in the bottom part. Now I'm taking the partial derivative of this expression with respect to y. So I'm going to get x cubed times 4y cubed times z squared. I would probably write that as 4x cubed y cubed z squared. And then minus 0 plus the derivative of 8 times the derivative of x times cosine of y is x times negative sine of y. So I'm going to get minus x times sine of y, and the derivative of z cubed is 0. So there's my implicit derivative with a lot less algebra, right? That's way easier to do than actually like doing it implicitly. All right, you all should take a minute to try and find the other one. I want you all to find del x del z. And that will point out that if you know it's negative fz over fx, you already know what the denominator of this expression should look like. It's the numerator right over there. So half of the battle is already over. You just have to find what fz is. Shouldn't be too terrible. You get song stuck in your head and just won't go away. I forget actually what the title is. It's sung by Nathaniel Rateliff. It's a jam. It's good. Yeah, I'll find the title. It's really good. I highly recommend it. Let's see here. So let's find fz first. So fz, the partial of this with respect to z is going to be x cubed times y to the fourth times 2z, or I would write 2x cubed y to the fourth times z minus 0 plus 0 minus 3z squared. The denominator we already know should be the same as the numerator here. It should be the partial of this with respect to x, which will be 3x squared y to the fourth z squared plus cosine of y. And that's really all there is to this formula. Yeah.
Like that thing, but today he was like, "Oh, if you leave it like that."
Mhm. What does he want you to do? Did he want you to like distribute the minus sign?
It's like same concept, but
I'm really curious.
yeah.
I feel like it's fully done here.
All this work. I thought this was like the final answer. He was like,
I would too.
is that the final answer? And all this was like, I was like, no.
Oh, no, this is a certain condition.
Oh, for this one? Okay.
Yeah, okay, this one's kind of special.
Okay, but if it doesn't give a, then it does.
Yeah, there is, yeah.
Hopefully.
I was like, yeah, usually that function's kind of interesting, but what's that? It's x cubed plus y cubed equals 6xy. Is that what it is?
Yeah.
And it goes to the point 3, comma 3.
Y x equals, or f1 equals, does not equal 0.
I see.
Oh.
Yeah.
Yeah, that's the condition.
Sure. Yeah, I mean, you might ask for more clarity from him, but as far as I am concerned, this is a perfectly good answer. Yeah, I wouldn't do anything else there. Now I'm gonna be able to look at that later because I'm curious.
Okay, so to read
Iterate.
English, if we want to find the implicit, you can just do this. And
Yes,
the hard way.
exactly. Unless someone specifically says they want you to do it the other way. But this is perfectly valid every time. The only thing you have to do first is make sure you write the entire left, like everything on one side, call that thing on the left your capital F, and then you want to find del X del Z, it's negative FC over FX. All right, we should continue to move forward because there's lots of other things to talk about. Let's talk about directional derivatives. By the way, just for those of you who didn't hear it already, I did post solutions on Canvas to the even homework questions from homeworks number 5 and number 6. Yeah, directional derivatives. So I will point out so far, we have been finding some directional derivatives. When you find the partial derivative of f with respect to x, you're finding the derivative in the direction of x towards you, if you're thinking about three-dimensional graphing. Or if you find the partial derivative with respect to y, you're finding the derivative in the direction of moving to the right. We're going to expand on that. But before we do that, a quick review of some 17b topics. The dot product. Definitely going to be featured prominently in a lot of what we do for the rest of the quarter. Maybe not so prominently, but certainly not going away. So if you've got two vectors, say, let's call them u and v. The dot product of u and v is really easy to calculate, not the way I'm about to write it. So there's a really easy calculation we'll talk about in a minute here. But if you've just got vectors, the kind of way we geometrically think about the dot product is it's the length of the vector u multiplied by the length of the vector v multiplied by cosine of the angle between those two vectors. But usually we don't know what the angle between the two vectors is, right? Usually we don't know theta. So the more typical way of calculating the dot product is that if, for example, u is equal to the vector with components a and b, and v is equal to the vector with components c and d. So just graphically, right, here's what this would kind of look like. I'll make sure everyone's on the same page here. When I say that u is the vector a, b, what it means is I've gone a in the x direction and b in the y direction from typically the origin, although technically it can be from whatever starting point. So if I was going to draw the vector u, I might say, here's my vector u, where I've gone over a length of a and up a length of b. And similarly, if I'm going to draw my vector v, I'd say I'd gone over a length of c and up a length of d. So the first component is always the x part. If it's positive, you go to the right. If it's negative, you go to the left. The second component is always the y part. If it's positive, you go up. If it's negative, you go down. And then your vector could be a vector with 3 components. It could have an x, y, and a z, and then it'd be like forward, left, or forward, right, and up. The nice thing about writing vectors component-wise like this is that taking the dot product of the two vectors is super duper easy. The dot product of u and v, if things are written like this, is equal to the number A times the number C plus the number B times the number D. That's it. So for example, if our vectors were, say, U equal to the vector 1, 4, and V equal to the vector 5, 2, then the dot product of U and V would equal 1 times 5 plus 4 times 2, which is 13. Couple things to remind ourselves of here. The dot product of two vectors is not a vector. The dot product of two vectors is a scalar, or just a real number. What else? I think that's what I want to say here. The dot product is also symmetric, meaning it doesn't matter which order you calculated it. If I were to instead calculate V dot U, which is 5, 2 dotted with 1, 4, that would be just equal to 5 times 1 plus 2 times 4, which is still 13. Just like regular multiplication, order doesn't matter. With dot products, order doesn't matter. Something else. Oh yeah. There's other notation for vectors. This is probably the notation I prefer, but if your teacher is using, has he talked about vectors yet in class? Is this notation he's using, or is he using something different?
You did I.
Okay, sure. Yeah, that's probably the other most likely one. So we could also write the vector U as I plus 4j and the vector V as 5I plus 2j. They're pretty standard. Oh, something in the chat. What's in the chat? For the back to the implicit. So by the way, if you guys see something in the chat and I'm like not seeing it, let me know, please. For implicit differentiation method, you have to set everything to one side and solve the partial in terms of each variable. Yeah. That's, you have to set everything to one side. Let's just go back and look for a quick second here. Right, you have to bring everything to one side like we did here. And then I wouldn't say, I wouldn't use the word solve there. I would say, and we take the partial derivatives with respect to the necessary variables. So when I was doing this right here, to find dy dx, I did negative fx over fy. The fx, I'm taking the partial of this with respect to x. For the fy, I'm taking the partial of this with respect to y. And I'm treating everything else like a constant. So when I take fx here, I'm treating y and z like constants. When I take fy here, I'm treating x and z like constants. That's what's happening there. And also, if you're on Zoom and no one is seeing that you've written something in the chat and we're like moving past it, you are also welcome to unmute yourself and say words. You might make me jump, that's okay, but you're really welcome to actually say words as well. Okay, yeah, let's build this up a little bit. So we're gonna take, we have a little bit of time here. We're gonna take some time to build up how the directional, because like I could just tell you the directional derivative formula. And I'm sure you all believe me and you'd be able to use it easily. But I would like you to kind of have just a tiny bit better idea of actually why it works the way it works. Because the idea is now, like if we're on this surface, instead of saying what's the derivative in that direction, or what's the derivative in that direction, I say what's the derivative in that direction, and why do we get what we get? So I need one more piece of kind of previous knowledge. Maybe previous, I don't know, maybe not. Maybe you've not seen this before. It's okay, it's not that terrible. I want to find the parametric equation of a line. In 3 dimensions or 2 dimensions. That's terrible.
All right. Dropping things.
Okay, so for example, let's say we have this line that goes to the points 1, 2 and 4, 7. And yes, you could certainly do a y equals mx plus b kind of deal, but the problem is that doesn't work if you have a line that goes through points in 3-dimensional space. If you have x, y, and z and x, y, and z, things get a lot dicier, and you can't, there is no y equals mx plus b. Instead of doing y equals mx plus b, you need a point, which we have, and instead of a slope, you need a direction, aka a vector. because a vector gives you a direction. So what we're gonna do here is we're gonna say, let's imagine a particle moving along the line from the point 1, 2 at time equals 0 to the point 4, 7 at time equals 1. So let's talk about how each variable changes. So in our line equation, we can say, well, x is going to start off at 1. Right, at time equals 0, we should get 1. And then 1 second later, x should now be 4. So I'm going to add on the difference between 4 and 1, which is 3 times t. So that when time equals 0, x equals 1 plus 0. Cool. When time equals 1, x equals 1 plus 3. And then, should have made this a little bit bigger. Another 1 second later, what should the x coordinate be? Well, if time is 2, what's x going to be? How much? A little bit more than 3. So when time is 0, x is 1. When time is 1, x is 4. When time is 1 more second later, x is going to be how much more? Right, it's going to be 7 total. You could either plug it in here and get 1 plus 3 times 2. But really, I want you to actually see more that you're going from 1 to 4, difference of 3. 4 to 7, difference of 3. The next one would be at time equals 3, an x coordinate of 10. Because you're just going to go 3 more. So every time the time increases by 1 second, the x value in this example increases by a value of 3. Similarly, how much are the y's increasing by? Well, from 2 to 7, I'm increasing by 5. From 7 to the next one, I should also increase by 5. So that should give you 7 plus 5, which is 12. And that means my y, my parametric equation for y is going to be 2 plus 5t. And then you could talk about the domain if you really wanted to. T could be any real number. T is in the set from negative infinity to infinity. That's not super important. Okay. So this is going to be, it's a little bit challenging, but not that bad. So let's imagine, do I have enough space here? Yeah. So here's one of my favorite surfaces. F of x, y equal to 9 minus x squared minus y squared. We've talked a little bit about this surface before. It's a downward opening paraboloid, like a parabola, but revolved around the z-axis. And it looks kind of like this. And I'm interested in the level curve when z is equal to 4. So if z is equal to 4, I have 4 equal to 9 minus x squared minus y squared. And if I add x squared plus y squared to the left, subtract 4 from the right, I have x squared plus y squared equal to 5. Not surprisingly, if I move up to z equals 4, and I cut this paraboloid surface, I'm going to get a circle. A circle whose radius is the square root of 5. So I move up to, 1, 2, 3, 4. And there's my level curve at a height of z equal to 4. And a curve of a circle of radius square root of 5. And very specifically, I'm really interested in the point 1, 2, 4. So that point there, 1, 2, 4 is forward, right, and up. Right, it's coming 1 out at you, 2 to the right, and then 4 up. We could probably draw it if we tried. See, kind of a little bit better now. Let me zoom in. I can zoom in. See how I've kind of gone 1 in the X direction, 2 in the Y direction, and we'll pretend like that's 4 in the Z direction. Okay, so now here's the question that I'm trying to answer. I'm at the point 1, 2, 4. And I want to know what's the derivative at that point. So what's the derivative at the point 1, 2, 4 in the direction, not straight towards you, not straight to the right, but in the direction that's kind of that way, in the direction of the vector 4/5, 3/5. Don't want to call it U or Z. U, call it U. Or 4/5 I plus 3/5 J if you prefer. So essentially what I'm saying is I'm moving in that direction, notably here, not up or down. I'm moving horizontally, parallel to the XY plane. I'm not increasing my elevation, not decreasing my elevation. I'm moving straight towards that direction there. So I'm moving like out that way. And then I'm asking what's the slope of the surface in that direction? So what's the slope of the line tangent to the surface moving in the direction of that vector? That's what we're going to figure out right now. Oh, and you can see that. So here's how we do it. We're trying to find the derivative. We're not finding the derivative using the chain rule. So check this out. Our function f is a function of x and y. But this line that we're moving in the direction of, well, we can parameterize that line. That equation, in fact, let me do another drawing to make it a little bit easier to see what we've got here. If I look in 2 dimensions for a second, if I look at my level curve, the circle x squared plus y squared equal to 5. There's our circle, x squared plus y squared equal to 5. We know that z is equal to 4 because we've gone up to a height of 4. And I want to look at the point 1, 2, 4. So x is 1, y is 2, and z, we're not graphing on this because, right, that's just how high we are. Z is 4. So there's the point 1, 2. And from that point, I want to move in the direction of this vector. 4/5 to the right, 3/5 to the up. Or essentially 4 right and 3 up. Or a little bit more right than I am going up. So maybe something like that. That's the direction of my vector u. So here's what we're going to do. We're going to parameterize the line that that vector goes through. So here's my line L. And we're going to do the same sort of thing we just did when we parameterized the line. We're going to say, okay, L, the parametric equation for L, well, the x part is going to be the x coordinate plus how much we're moving in the x direction. Well, we're moving over, in fact, maybe I should have written, right? We're moving over 4/5 and up 3/5. So to get from this point to that point, I'm going to take my x value of 1 and I'm going to add 4/5 times t. And I can keep doing that, right? To get from there to there, I add 4/5 and then another 4/5 and then another 4/5 every time t increases by 1. Similarly, y is going to equal 2 plus 3/5 times t. I'm always happy to stop and clarify things if you have questions. So here's the deal. Check this out. F is a function of x and y. But what are x and y both functions of? T. So if I want to find the derivative of f with respect to t, it's going to be the partial of f with respect to x times the derivative of x with respect to t, plus the partial of f with respect to y times the derivative of y with respect to t. But now, looking at all the things we've got here, so I'm trying to squeeze everything on one page here. Our function f of x y is 9 minus x squared minus y squared. And our actually I actually don't want to fill in the things just yet. I want to simplify this expression a tiny bit before we fill anything. So I'll point out that we could write this as a dot product. This is the dot product of the following vectors. The vector del f del x comma del f del y dotted with the vector dx dt comma dy dt. Okay. The vector of partial derivatives of your function in order is called the gradient of f. So this thing right here, this is the gradient of f. It is a vector. And it can be the part, so basically, it's all the partials that make sense. If f is a function of x, y, and z, then the gradient of f is a vector with 3 components. That's the partial with respect to x, comma the partial with respect to y, comma the partial with respect to z. They're always in order. You would never write it as like fz, fx, fy. It's always in the correct order. And then dx dt dy dt, well, if you take the derivative of this with respect to t, what do you get? You get death to a bug. Sorry. That was violent. I apologize. It's just I wanted to write on my paper and it was right there. Just a little sorry, bug. I'm sorry. You probably weren't cool, but you're dead now. So okay. Anyway, dx dt is 4/5. Right, taking the derivative of this with respect to t. And dy dt is 3/5. Or in other words, this vector here is the vector that's the direction we're taking the derivative in. Right, when we posed this question, I said, I want to find the derivative at the point 1, 2, 4 in the direction of the vector 4/5 comma 3/5. It's not a coincidence we're getting this. So what we really are getting here is we're getting the gradient of f dotted with the vector that's the direction we're taking the derivative in. Notably here also, the vector u is a unit vector. If you look with, and I'll remind you, a unit vector is just a vector that has a length of 1. So if you were to find the magnitude of the vector 4/5 comma 3/5, it would be the square root of 4/5 squared plus 3/5 squared, which is the square root of 1, which is 1. If you don't have a unit vector to start off with, you just turn it into a unit vector. But now what I want to say here is that this is, I forgot the symbol there. This is the directional derivative. The directional derivative of my function f in the direction of u is equal to the gradient of f dotted with the vector u. This is our directional derivative. The directional derivative of f in the direction of u. We should actually still calculate this, all right? We're not done. So to actually calculate what we're finding here, the gradient of f, well, our function was 9 minus x squared minus y squared. So the gradient of f is equal to, well, the derivative with respect to x is negative 2x. The derivative with respect to y is negative 2y. I'm dotting that with the vector 4/5 comma 3/5. typically we plug in the point before we actually do the dot product. So this would be the directional derivative at any point in the direction of u, but I want the directional derivative specifically at the point 1, 2, 4. So I should really say, I'm gonna evaluate this at the point 1, 2. I'm not writing the comma 4 because that's the z coordinate, which doesn't really matter here. This is gonna end up being, if I plug in 1, I'm gonna get -2. If I plug in 2, I'm gonna get -4, dotted with 4/5, 3/5, which is equal to -2 times 4/5 plus -4 times 3/5, which ends up being -20/5, which is -4. What this says is that on this surface, at this point, if we move in the direction of the vector 4/5, 3/5, the slope of the tangent line of the slope in that direction is -4. A lot. That's what it is. Like, no, that's right. Okay. Which means we're going downhill, right? If the slope is negative, it means you're going downhill. And then I will point out, because this is a useful thing, if you turned around and said the direction was the opposite of what it was, which is -4/5, -3/5, then the slope of the tangent line would be +4. Because you're just going along in the same direction, just the opposite way. So instead of like walking down the hill, you literally turn around and you walk up the hill. So if you ever go in the opposite direction, the slope just changes signs from positive to negative or negative to positive. Which I think is kind of neat. How much time have we got? Not a lot. Okay, so let's do one more example here. Yeah, not that one. Do I have any other examples? Sure, let's look at this one. So let's say our function, say we have f of x comma y is equal to 5xy squared minus 4x squared y. And we want to know what is the derivative of f of xy at the point, sure, let's say -1, 2 in the direction of v equal to 5, 12. So one thing to point out here is this v vector, this direction vector I've given you, doesn't technically qualify as a direction vector. Even though if I said go in the direction of 5, 12, I think you'd all know what I meant. You mean go over 5 and, or I should say, go forward 5 and right 12, if you're thinking in the XYZ coordinate system. But if someone says they want a direction vector in this class, they typically mean they want a unit vector in the direction. And the reason why is because I don't want you to say 5, 12 and you to say 10, 24 and you to say 15, 36. All those vectors point in the same direction. I would love it if everybody gave me the same answer. That's why we typically ask for a unit vector, because it makes it so everybody has to give the same answer. So that's what we're going to do here. So if I want to find the directional derivative, well, I need to find my gradient and I need to find my unit vector u. So let's find u first. So u is going to be, take your vector v and divide it by its own length or magnitude, if you prefer. So that's going to be the vector v, which is 5, 12, or 5i plus 12j. I've gotten so used to writing it in this notation, but I'll try to start using the j notation. Divided by the square root of 5 squared plus 12 squared. Right, the magnitude of a vector is just the square root of the squares of its components added together. So that's going to be 5i plus 12j divided by 25 plus 144 is 169, and the square root of 169 is 13. These numbers often come up, by the way, 3, 4, 5, 6, 8, 10, 5, 12, 13. So my unit vector u is going to be 5/13 I plus 12/13 j. My gradient, on the other hand, the gradient of f is just going to be the partial derivatives in order as a vector. So it's going to be the derivative with respect to x, that's going to be 5y squared minus 8xy I plus the derivative of this with respect to y, which is going to be 10xy minus 4x squared j. But then we actually want to plug in the point we're trying to take the derivative at. So the gradient at the point -1 comma 2 is going to be 5 times 2 squared minus 8 times -1 times 5 in the I direction. I didn't give myself nearly enough room here. Plus 10 times -1 times 2 minus 4 times -1 squared in the J direction. That's going to be, let's see, 5 times 4 is 20. 8 times 5 is 40. 20 plus 40 is 60. I, and then 10 times -1 times 2 is -20. Minus 4 is going to be minus 24J. Kind of gross numbers, but some of these are gross numbers. So then my directional derivative here is going to be the gradient of f evaluated at -1 comma 2 dotted with my unit vector u, which is going to be that dotted with that. So it's going to be 60i minus 24j dotted with, and do make sure you emphasize the dot in that dot product there. It should look really strong. 5/13 I plus 12/13 j. I know it's 201. Let me just finish this here and I'm done. So then you're going to get 60 times 5/13 minus 24 times 12/13. A number, right? Not a vector, a number. This number that represents the slope of the tangent line in the direction that you're traveling on the surface. You can simplify this a bit. It's 300/13 minus, what's that, 288/13. So you end up getting 12/13. The reason I was able to do that so fast is because 12 times 24 is really 12 times 12 times 2. And you know that 12 times 12 is 144, and 144 times 2 is 288. So it's not that special. So in the direction of that vector on that surface, the slope of the surface is positive 12/13, which means at that point on that surface, you are going uphill, not down.